Welcome to our embedded system app of the day. I don't know if you are aware of this, but I am kind of doing an embedded app of the day for those of people in TV land. And so today's embedded app of the day is this. What is it? It's a board. Very good. What kind of a board?
It's like a
So the first thing that comes that what's the first thing you notice when you look at this board?
It plugs into something.
It's like
Say that again. It plugs. All right. What else?
It's in internet.
You notice it's kind of orangey. And well, there's a reason why it's orangey. If you look really carefully, you know this is the top of a cap, right? And the top of a cap is usually silver.
That's sealed.
So it's sealed. What sort of applications do you think of where you need sealed things?
High humidity or water.
Communications.
All right, where there might be water or moisture or great changes in temperature and humidity and stuff like that. What application do you think that encompasses?
Automotive.
Automotive. Ding, ding, ding. Who said that? All right. Have you had a trip to the price closet?
No.
All right. You get a trip to the buy price. Oh, you can get it right now. If you want to, you can come get it right now. I don't mind. And so this is an automotive controller board. Now the big question is, what does it control? So if we look at some of the things that are here, and then this is the start to doing reverse engineering. So if I look really carefully at this, or I didn't turn on the light, that would have helped. Okay, maybe not. We have this this chip here, and you know what? You really can't tell what this is. And it has very nondescript names. Oh, here's something here. It says NEC. Copyright 1995, 98, something like that. Oh, then it's got some 2000 thing on it. So NEC, this is a chip that says NEC on it, and actually if you look at it, it's really thick with this gooey stuff on top of it. By the way, NEC is what? Nippon Electric Company.
Japanese.
All right? Who bought NEC? Renesas. So, the Renesas board that you're using in class basically is an offshoot of that processor there. So, in other words, one thing I've mentioned before is that Renesas processors are the most common microprocessor in the world. Here's an application. NEC is the one of the three predecessors of Renesas. The other two being what? Mitsubishi and Hitachi, right? So, if we look at some other parts of this board, here's a ST microchip. Just looking at the number of pins. Oh, look at that, the chip was made in Malaysia at least. It is most likely is being used as some sort of a transistor, something, transorb, I don't know, something. I'd have to look it up. But a lot of connectors, and one thing to note about these connectors is they're color-coded and they're locking. And so when you get into the automotive industry, there's a lot of vibration, so you have to make sure that you have connectors that lock. And then the other thing I mentioned is that there are different colors. I can bet you that the plug that plugs into these connectors are probably also color-coded, so that when they're assembling, it is really easy to identify the black plug goes in the black connector, the white one goes in the white, and the blue goes into the blue. So manufacturing engineers and for people like you who will specify how things are manufactured, will specifically make it as easy as possible for anybody to assemble this, all right? And if we look at the back, lo and behold, it tells me what it is. likely something that was specified by BMW and that United Technologies Automotive actually manufactured for them or specified and manufactured for them. What kind of car does it come off of? Anybody want a quick look on the web to see where it comes from? But you'll notice that it looks, if you look at the way they have this coating goo, it seems to be really thick down at this end and not as thick up here. So what I figure is that in their processing, that they take it like this. It's better shown up here. So they take it like this and dip it in some sort of coating material, pull it out, all the excess drips towards the bottom. But still, nearly every single electronic part up to the connector is coated in this orange goo. So, as an example, this is one of the many microcontrollers that will be available in the system. I don't actually think this is for the engine control unit. I believe somebody mentioned that this is for the climate control unit inside the automobile. This was given to me by one of my students last semester who apparently wrecked the car that this came from. This was what they were going to replace, and they just gave up and gave it to me. This actually came in a box that was about as big as this device was. The box meaning a plastic enclosure, and so that plastic enclosure bolted some way into the vehicle. All right? So, this is today's embedded app of the day, which is a BMW controller board. This is ECGR 4101, 5101. This is going to be lecture number 11. Lecture number 11 is going to cover analog to digital computing. And I'm going to start it off with some generalities and some general concepts. And the first thing I'm going to say is, you live in an analog world or a digital world? What's the answer?
Analog.
Okay, who votes analog?
Tron.
Who votes digital? You got to vote one or the other, or who votes analog? Who votes digital? All right. When I talk right now, can you hear my voice via digital or analog?
Analog.
All right. Even though I'm talking into this, the amplifier most likely is picking it up as an analog signal. Analog electricity is modulating, is vibrating some speaker here, or other speakers up there, and you're hearing sound pulses, and that's an analog world. So nearly everything that is sensed in the world is going to be analog. But a computer has difficulty computing analog things because it's a digital machine. Now, some of you in here will actually invent and work on analog computers. And in fact, analog computers are not a new concept. They've been in existence for tens of years, 50 years maybe. But the popular ones now are digital because they're a lot cheaper, consume less electricity, and to some respects are faster, although analog computers pretty much in the research world can outperform digital, but they're not prevalent yet, but the point is yet. So let's look at analog. This is an analog world. So, what is important for us to measure in life? So give me some ideas. I heard
Success.
temperature, velocity. Did I say happiness?
Age.
Analog world. I heard humidity. think I heard it, or maybe I just heard a voice in my head. What else? Yeah, also, several people at one time I didn't hear you can hear it. Pressure. Have we done this already? I can say that again? Robotics. Oh, and robotics. See, I'm starting to forget what I'm actually covering this material. That's a sign of getting old. What else?
Distance.
For all intents and purposes, we could also call this time.
Signal strength.
Power. Signal strength, RSSI, right, is power. So, just an example of all of this. So, in many of these cases, you're going to be provided, or you're going to provide a sensor of sorts that you can use to measure something. So let's take a look at one example. And to do that, I can just do a simple web search. Ooh, let's open up Chrome. I've never opened up Chrome before. I like this. What do you want to open up the Chrome thing with? Oh, Chrome.
You should open it with Microsoft Paint.
Yeah, no, I'll go back to the Microsoft. I guess nobody wants me to do Chrome. Firefox is open source, right? What the heck? Alrighty. I don't believe I'm running it. Chrome doesn't want to run. Ooh, this is just downright creepy.
Internet Explorer.
I think Microsoft has been messing with this PC too much. It keeps everything else from running. What the hell is this thing on the screen? I don't want to do that. All right, so this is funny. We'll go to Chrome. How come it doesn't come up with Google?
The bar is Google.
So let's look at some of the sensors. So if I want to say temperature sensor, one-wire digital temperature sensor, SparkFun. By the way, everybody familiar with SparkFun? SparkFun is one of the best sources of wonderful parts to use for hobbyists and everything else. So here you go. It is this big. It's nothing more than a chip. You are literally giving it, oh, look at this. What does it say? 9 to 12-bit precision. What does this mean? We have an interesting situation with this. I can do one of two things. I could provide a device here that uses analog. So in other words, you give it a voltage, VCC, and then you measure whatever is on this leg. Or, with this other part I just identified, I give it VCC, I give it ground, and on this single wire right here, it's going to provide me with a serial communications signal. And I'm going to get from 9 to 12 bits of precision. So that means what? That this device here has inside of it a microcontroller and an ADC inside of it already. And when you send it a control signal, most likely the control signal is going to be instruction hex F2 or something like that. In response, the sensor is going to come back and tell you what the temperature it is that it's reading via either 9 or 12 bits of precision. So this already has an analog to digital converter inside of it. And this is pretty common with the way that things are going now. By the way, if you look at this, this document here, it talks about one wire Maxim IC. So Maxim is a company that actually has its own, I think it's the former Dallas Semiconductor company. It has its own protocol for communications, and it uses one single wire for the communications to be transferred back and forth. And then it needs, of course, VCC and ground. But if we were to look here in this wonderful place, wow, look at this, cameras, little itty-bitty cameras. Look, one of the cheapest things. Now here's a good example, mini photocell. So this mini photocell is nothing more than 2 wires and a big resistor. And it's a photosensitive resistor, so when you put a light on it, the resistance value will change. What does that mean when resistance changes? So let's take a look at an example. If we have this wonderful device here, which is a light sensor, and I provide VCC to this, what am I going to measure?
Current. Voltage drop.
Do I want to measure current or voltage or what?
Voltage drop.
Voltage drop. Okay, so I'm going to hook this up to a pin, right? So if I shine lots of light on here, my voltage at this point is going to be what?
You need to measure current.
Oh, current now. Now you want me to measure current.
You need to add another resistor.
Now what?
You need to add another resistor.
Oh, so this is not what you want to do. You want to use what's commonly called a
Voltage divider.
voltage divider. So you provide with this light sensor and then what you do is you measure this resistor value is something known. Let's say it's 10 ohm or 10 k ohm. And then you measure this point here, right?
No, the center one.
So maybe you would hook it up to port. That's an R there. That's a T. Can you tell? You'll hook it up to port 2.5 or 2.0 or whatever. So how do you know what this voltage is going to be, or what this light intensity is going to be?
Through ADC.
All right, so that is, well, let's think about, this is the problem that I'm going to do. I'm going to have a light sensor here. How do I use this? Does anybody have an idea how you would actually determine what the voltage is? And then you can teach the rest of this class. Who knows? Oh yeah, look at it. They know this. How about anybody else? How many is this new? I want to make sure I'm doing something new, right? That you haven't done this before. How many have seen this before and know what to do? All right, a couple of you. Wow. One ET and none of the other ETs? What is that? Yes, no? Or are you just smarter than everybody else? Yeah, okay. So let's step back a little bit and look at the theory behind an analog to digital converter. So we're going to start with why you need to convert things into digital. So, in the real world, we'll have an analog signal coming in, which we'll call Vin. And we'll have our device here, which is called our analog to digital converter. The whole idea is that we have a range of voltages in here. And what we want to do is we want to convert it. And I'm just going to show 4, actually. I'll show an unknown number. And we'll want to convert it into digital, which is something that we can look at. So, as an example, let's say our range of voltages is going to be 5 volts to 0 volts. And let's say we have over here, we'll say that we have 8 bits to represent this voltage. We've already seen a problem like this in an earlier chapter. I just glossed over it really quickly. So what we're saying is that when you have the value 5 volts, that it's going to be the biggest 8-bit number possible. 1111, 1111. And it's going to go all the way down to 0 volts, which is going to be 0000, 0000. And where it ends up in the middle is going to be due to each of the individual steps. Now, do we know what the range of voltages is going to be for this, just as it's drawn? Usually not. So what we need to do is we need to add what we call reference voltages. So we need the voltage reference plus. So that will say this is going to be the highest voltage. And we're going to add a voltage reference minus. That's going to be the minimum voltage that we could ever read on Vin. And that's how we will determine what our upper end and lower end is. Now it could change. For example, we may work with a chip that only runs from maybe 3.3 volts to 0 volts. And so we would put that on here. Now the default for our processor is, what is our default for the current Renaissance processor we're using? What's the low voltage? 0 volts, right? What's the high voltage? I think it's 3.3, because the chip runs at 3.3, right? Ah, you're going to pull it out and check it, aren't you? Good. And if I'm wrong, do you get a trip to the price closet? No. No? All right. Now, in our specific system, typically what you will do is that your Vref plus and your Vref minus are hardwired. And you really don't change them much for your particular embedded application. Now the other thing that you also have to do is, a priori, you have to identify which ports will serve as your VNs. Now you can measure all sorts of different voltages, and you can bring them into all sorts of different ports and pins. Because don't forget, if you have your processor and you identify port, I'm trying to think which port we use for A to D. I think it is A, but I'm not positive, so I better check first, right? AN, you know what, we're just designating it as, we call it AN0. And we can have it go all the way up to AN7. So there's a capability of 8 analog signals that you can measure. So you can hook up all sorts of different analog devices. Look on your board. What do you see as an analog device that goes in? All right, there's a potentiometer. I believe the microphone actually goes in as an analog device. What about the accelerometer? Right. The accelerometer is actually on a digital serial port. I believe it's SPI, no, it's I squared C. And we'll actually go into that in the next chapter, chapter number 7. Can you think of anything else that's analog on that board? Do we have any light sensors? How about the push buttons? Isn't that an analog signal?
No.
Usually push buttons are not, because with a push button, we actually rely on the button and a resistor to give you either power or ground. Hey, you know what? This might be a good quiz question. This might be an excellent multiple choice question. So, if I were you, I would look up all the detail about your board and see where the analog ports are going in. Or should we look at it ourselves? Shall we do it now? Why not? All right. Today we are going to continue our lecture. And remember, we're on lecture 11. And I believe this is going to be page, in fact, I'll just continue reading on this page. So what I want to cover is the general concepts of analog to digital conversion. How many of you in here are familiar with A to D conversion, everything about it? Raise your hand high. All right, again, this was hardly anybody. So we're going to start going into some of the basics. I'm going to go into the basics a little bit more on the theoretical side, and then what you can expect when you're doing something else. So here we started as one example, I should say, or the general concept was as follows. That you have some sort of A to D converter, and let's say this is a part that is manufactured by TI or Analog Devices or someplace like that. You have a single signal coming in. This is the maximum, this is the minimum that that signal could ever be. And then you're going to have some digital outputs. Now, in the case of a simple accelerometer like I showed up here, hey guys, I can't do this if you're talking because it picks up on the camera. All right, so if you have a accelerometer as an example, how it would be in your circuit is your accelerometer would have supply voltage VCC, it's ground. Remember I said X, Y, Z, but that would go to another chip, which would typically be sent to VCC and ground. And then it would have, let's say it was a 8-bit ADC. You would have your lower data bits all the way up to your upper data bit. And if this were an example of an 8-bit ADC, obviously the accelerometer's values would be somewhere between 0 and 255, right? So a total of 256 different values. And you would have to have another ADC that was also connected to VCC and ground, and it would have 2, 3, 4, 5, 6, 7, 8, its own values to D7. By the way, these would be passed into your microcontroller. Some port, whatever the port is, right? Now, here's the thing that makes it life a lot easier. Well, instead, what we're going to do is we're going to have our accelerometer I like that better. We're going to have our accelerometer and we're going to have the X and the Y and the Z go into our ports, maybe we call it AN0, AN1, and AN2. Of course, this has VCC and ground as well. So the whole idea is that now inside of your microcontroller, you're going to have that analog to digital converter. There we go. That looks better. So now let's see what happens inside the analog to digital converter. Well, inside your analog to digital converter, you're going to have a certain amount of circuitry available. And this will be an example of that. This is in your book. Remember I said AN0 to AN7? There is some internal circuitry that will have an impedance converting circuitry. This multiplexer will then go into a sample and hold circuit. Sample and hold meaning that an analog signal could be varying quite a bit. So at one point in time, we'll just say, all right, that's my snapshot. I'm going to take a picture of that. In other words, I'm going to hold that voltage, and then I'm going to do some converting. And then it's going to go to the controlling circuitry for comparing. And then once it's compared, it'll go into, it'll be stored into your system. Now, I should say it will be controlled into your registers. So now I guess this is the best time to take a nice assessment of what is a good way to actually determine what your voltages that you're reading. And the best way to do this is by saying, for a trip to the prize closet, I need somebody to do some guessing. So I'm going to have a guessing game. And my request to you is to find a number between, let's say, 0 and, I don't know, let's say 255. And I'm going to write the number at the, this is horrible, what is this brightness? Oh, look, I like this. The brightness was 120%. All right, so find a number between 0 and 255. I'm going to give you 8 guesses for a trip to the prize closet. And let's see, who do I choose to do that? Who wants to play the game? You've seen this one, so you hush.
How
Right?
do the rules
Anybody in
of
robotics
games
has
work?
seen this game, so hush.
It's kinda
All right, we have somebody. You're ready. Yeah, you. All right, stand, you got to stand up though. And you're not in the video, so they can't tell you. All right, so let me think of a number. I'll have to write it down at the bottom of the page. All right, you see the number I wrote down at the bottom of the page? Good. So go ahead, tell me what. Oh, and in the process of telling you what the number is, or guessing what the number is, I'll let you know if it's higher or lower. All right, does that make it easier?
Yes.
Oh, okay, great. What's your first guess? 60. 60. 60. It's lower.
20.
It's lower.
10.
It's lower.
2.
It's higher.
5.
It's lower.
4.
6. All right. You said 4. It's lower. It's higher. 3.3. Congratulations. You have a trip to the prize closet. Your second time. All right. Now, let me tell you, you got a lot of those. All right. Because it could have been that you didn't get it right. So I'll do it again because I'll see if anybody can guess it more methodically. All right. All right. So who wants to play this game? All right. We have you got a trip to the prize closet yet?
No.
No. Okay. Go ahead. All right. So what's your first guess?
127.
Ooh, 127. It's higher. Now you got to do the math, right?
Yeah. 185.
185. It's lower.
Wait, a second.
You can pull out a calculator. That's relative.
150.
150.
Yeah.
It's lower.
138.
138. It's lower.
132.
It's higher.
125.
It's lower.
133.9.
Okay, now hold on. All right. So how many numbers could it be right now?
2.
All right. How many guesses do you have left?
2.
Not bad. Huh? All right. So your next one is
133.
133. It is lower. You got it. All right. So this is a good example. Oh, by the way, in case you didn't believe me, I wrote it at the bottom. There's 133, and oh, by the way, I just wrote 3 for the previous one, right? I just added 33 since I was a little lazy. So you get a trip to the prize closet. You're the third person in line. So again, let's look at the first way the person did it. You didn't really think about splitting each one of the guesses in half, right? Who guessed? Oh, you, that's right, you did.
No,
So,
that was a standard thought.
so it was possible that you didn't get it, you might not have gotten it, right? Yeah, in 8 guesses. But in the second option was the, oh yeah, what we did is we split the entire range in half. And then when you found if it was higher or lower, then you split that range in half. And then when you found if it was higher or lower, then you just kept on dividing, right? And obviously, using the second method, the most times it would take you to find the number would have been 8. All right? Just the way it worked out, it was 7 in this case. If I had guessed the number, or if I written the number 127, you would have got out of the first guess, right? But you have to work for the worst case. And actually, that's the best way to methodically do it. Now, why do I mention that? That's exactly what a successive approximation algorithm does, and that is what our hardware will be doing. So if we were to look at, I'm trying to pull up a nice picture of this. I think I'm only going to be able to do a picture of it in the book. And so this is nicely identified in the book as follows. In this case, the successive approximation approach would have resulted in, he started out with 0, or in other words, he started out with the number 1111111. So if he actually had chosen, or 0, 1111. So if he would have chosen 1 in there, which would have been 128, then that would appear closer to this. But after that, it's pretty darn close, right? So you identify. All right, here's my first guess right here. Is it higher or lower? Well, it's higher than that. So you put a 1 in the first bit. And then you say, all right, here's my guess. My next guess, I split the distance in half. Is it higher or lower? It's higher. So now I know what the next bit is. All right, so I said I'm going to split that in half. Is it higher or lower? It's lower. So then, again, you just keep on going down until you get to this point. Now, look at it. This picture is not close to what I would have drawn. So I'll have to have this fixed in edition number 2. But the whole idea is, in fact, I think they really messed this one up when they look at it. Yes? Well, I'll tell you what, we'll leave it with this one, all right? Because that's the one that's in the book, and I'll work with that. The whole concept is that you, and in fact, in my notes of this, I'll put it in my notes of this so you'll have a better idea, a cleaner one of these. But again, it's a successive approximation. You're splitting the guess in half. That is what's being done by our ADC. One thing I could add on top of this is there are other ways you could do it. You could do it with a resistor ladder, in which I think rather than just describe it and show it, I'll just say by having several resistors together with voltages as it goes through, you're making comparisons with comparators between 2 voltages, the input one and the one at that point. So this is just the way it does. It actually is one of the fastest ways to do approximation of what your data is. So what would happen is that if we had a voltage, and again, you know, the number is that you see over there is representing something like a voltage. So let's look at what like a voltage is. And again, if you've seen this in the past, and this is getting a little bit slow, let me know. And I've shown a drawing of this earlier. There is a direct relationship between the voltage and your digital code that you're going to have come out. In that, if we are going to use, let's say we have a 4-bit ADC. That this value down here is 0, 0, 0, 0. This value here is going to be 1, 1, 1, 1. 16 individual representations. If we have a voltage of 0 down here, and we have a voltage up here of 3.3 volts, one thing I know is that halfway in the middle is going to be 1.65 volts, right? So my expectation is that the digital value right in the middle is about 1000. Is that correct? Yes? Yes? What you will have is a step function. Oops, we only have 4 steps in between, so I should probably make sure to draw it correctly. So in this position, you will have specific steps associated with, oh man, I am butchering this. Associated with the compared voltage with the digital code. This almost looks like a table, but we're going to rely on the following. Inside your ADC, you are going to have the following formula. Is that your specific code N is going to be equal to whatever your input voltage is, minus whatever your negative reference is, total possible codes you could have, or the maximum value, is going to be 2 to the n minus 1. All of that is over whatever your maximum reference is, minus whatever your minimum reference is. Thank you. And then we have a rounding function in here. Now, in our case, and what we've discussed before, Vref minus is almost always 0. It doesn't have to be, but we'll make it because that's the way we can make it easy. Oh, by the way, I'll just say, again, n is equal to bits in our ADC. Vn is equal to the input analog signal, which will be sampled. And our Vref plus is going to be equal to the highest voltage Vn could be. In the same way, Vref minus is the lowest voltage Vn could be. So again, we'll just simplify this. N is equal to Vn, 2n minus 1, over Vref plus, and we'll take the integer of this. We've already gone over this, right? But this is just a recap. So let's say, for an example, if we say that Vn is equal to 5 volts, you know what, just for grins, I'm going to give us a Vref plus, and I'm going to give a Vref minus. Just so you can practice this. So the question is, what is N? Oh, by the way, also also have to say, what sort of precision do we have? Our precision is 12. So that means we're going to have an ADC that will generate 12 different, or that will have 12 bits to represent the number. So using the formula, we could say, well, I should say, what is the max that n could be? So what's the max that n could be? Little n. All right, 2 to the 12 minus 1, which is what? 4,095, right? What is the minimum n could be? Is equal to 0, right? So in the case of the max, n is going to be 1111, 1111, 1111. The min of n is equal to 0.0000000000000. In this case, the max is going to be when the voltage is 10 volts for the input. The minimum is going to be when it's negative 10 volts. So your job as a your job now is turn to your neighbor and say, given what I've given you right here, what is n?
208.
Well, you've already determined that. All right. So what is n? I'm going to give you just a couple of minutes. Please do that. What is n? And then give it to me in both decimal and give it to me in hex. By the way, you do have this already, right? All right, which part of this slide do you want, the top or the bottom? Oh, here about this. There we go. How about that? Is that good enough? All right, go ahead and work on that. And you never know when this might be on a quiz at the end of class. William Weissenkerber, Elias Noel, Karthik Krishnan Raju Kolapati, Mr. Solution, Lance Bennett, Eduardo Sete. Lance Bennett. All right, who has the answer for me? What is n equal to? No, that's all here. How about the answer is 307. 302? Oh, 3071. And then I heard 3072. Who votes 3071? Who votes 3072? Oh, wow. Why do we have a half the class there and half not? So I guess what? We're going to do it. So, in our situation, not likely. N is equal to, N is what? 5 volts, right? Minus what's my reference? -10 times 4,035 all over 10 volts minus and minus 10 volts, right? Plus 1/2 and take the integer of that. Hey guys, if you're all talking, this can't get recorded, you won't be hearing it later, right? So obviously this is 15 over 20 times 4095 plus 1/2. And so that's where I pull out my handy dandy calculator. Wow, you think that this is controversial. Everybody is all murmuring about it, all right? 15 times 4095 divided by 20 plus 0.5. So, the answer is going to be 3071. Right? Because it's 3075. And you take the integer of that, which is 3071. And don't forget, we added half that more or less are rounded. And then what is the hex of this? BFF? No way. All right. So in other words, 5 volts is your best friend forever. I swear I didn't know what that was, right? So inside of our microcontroller, if this were the case, then our answer that we would work with is 3071. All right? And again, it's 12 bits. That is just too funny. Now, what I would like to do is to talk a little bit more about, all right, now that we have our concept of ADC, now how are we going to use that? So again, remember in our circuitry, we have our control circuit, includes the decoder. I want to point out a couple of pins here that are important. Number one, the external trigger. When you're doing an analog to digital measurement, in fact, here, I'm going to step back a little bit further, and I'm going to say, if we want to do in our microcontroller an ADC, an analog to digital conversion, what are the types of things that are important? So if we want to perform an analog to digital conversion, what do we need to know? So, what do we need to know?
Sampling rates.
Say that louder.
Sampling rate.
Ooh, how frequently, right? What's another thing that's important?
Step size.
Step size. That step size is mostly associated with how big is how precise will I measure? For example, maybe 10 bits, maybe 12 bits. What else?
Resolution.
Well, that's my, resolution with respect to bits, or resolution with respect to frequency.
Bits.
All right, that's right here. How precise will I measure?
Conversion time,
How much time what?
it takes to convert.
Ooh. How fast can I measure? How about that? Yeah.
Type of quantization,
Type of quantization. Be a little bit more specific.
some rounding off. There are methods to round off.
All right. Rounding off. Is that something you can control? That's a good thing to think about. But that's usually controlled by the hardware of the microcontroller or the ADC. All right. But these are things that you can ask, that you can control. What else?
Range.
All right, range of the input. Range of values. You know, the upper and the lower. Okay. Yes.
Encoding technique.
Encoding. Okay, give me an example of what you mean by encoding techniques.
After getting the sample values, we need to put them in the order and then pass it on at the serial order. The type of encoder that we need.
So I think maybe you're saying more of, are you looking at one input or several different inputs?
Several inputs to one output.
Okay. Well, we're just doing several different inputs. So how about this? Which channels? Because I noted that there is AN0 to AN7, right? There's a possibility of 7 different channels. There's actually different ways you can measure that. You can do one at a time and only one ever. Maybe 2, you measure one, then the next one immediately right after it. Or you can just do a full sweep. You do AN0 through AN7. And just do all of them as fast as possible. All right. What's another thing that you, as a user of an ADC, that you need to know when you're writing your code? All right. How are you going to store it? Or pull it out? I'll put that on the side because that's something after you've done the setup and reading of it. Yes?
Threshold voltage.
You guys speak up on that one?
Threshold voltage.
Threshold. I'm not going to go so much as saying threshold, but maybe you want to sample and hold it. Is that what you mean? All right. Let's see, how many have not done it? How many times? Oh, so then I'm going to add a few more. How many times? As I said, you could set it up where you just say, just give me one value. Or you could say, all right, I want you to continually do this forever. And then maybe one last one is triggered on what? possibility for you to actually rely on your own system clock or something external. You could have an external clock that will cause you to perform an A to D conversion. Maybe a more precise clock. Maybe something like a watch crystal that runs at 32 kilohertz, which is a lot less frequent than what your regular microcontroller is running at, which is what? Oh, here. Okay, I heard 12 in the front.
I think it's 12 meg.
12 meg is the crystal. But I believe it actually multiplies that, right? Pardon me? You give up? The processor actually can run a quadrupler, so it can go up to 48 megahertz for our particular chip. So, these are the things that you want to ask. Now, remember how we said in before that we have a certain number of processes that run? Processes, or I should say there's some things you could do to set up registers. Right? You can set up registers in your microcontroller so that you can do certain things with other registers. So what we're going to look at is for our ADC conversion, you're going to want to do the following. You will want to initialize your ADC control registers. So there are several control registers which are really important for you to understand. Things like how frequently, which bits are you going to be looking at, or what's going to be the conversion rate. In other words, things that you set up will be how frequently do we sample, how precise. What is the range of values? Which channels sample and hold, how many times, etc. So if you look at your data sheet for an ADC, you'll be able to see how you can choose this. And so this is where I want to go off to the manual. Now the book itself has some ideas, right? But let's put it this way. This book is tuned to your controller that you're using for your board. So it is by far better to understand how to read that in the manual. How many of you have actually opened up the manual to look at certain things inside? Yeah, okay. Let's take a look at it. How many of you actually know where the manual is? All right, for a trip to the prize closet. How many pages are in the manual? About?
43.
43. In the back?
350 something?
No.
No.
All right, you give up. It's over 1,000. How many of you are going to memorize all the 1,000 pages
I got you.
for our test coming up in 1 week? Oh, yeah.
It's open book, right?
That's why it's an open book, open notes test. So, if you go to our board, manuals, Renaissance, PDFs, English, and this is in your stuff. And this is where I start trying to figure out let's see, where is it? Oh, for heaven's sake, this is going to take forever. Jump, this is not it. I think this is good, man. All right, here we go. It is, oh, look at that, 2,020 pages. And your first response to that is, oh my gosh, I'm not going to read all this. And the answer is you don't have to. You only have to read the part on ADC. So here we go. If we go into our manual, we're going to go down through and look for that section which says analog to digital conversion. Look at all this wonderful stuff that you can read about. I mean, just alone, interrupts is covered in 50 pages. Buses, everything you want to know about those reds or the yellow school buses, including the short ones I think you mentioned earlier, right? You guys are so irreverent, I tell you. DMAC controller, data transfer, I/O ports. You know what, I can just look at the side over here and look for ADC. So do we see anything here that says analog to digital converter? Here we go. Let's just go to the 10-bit A to D converter. 10-bit A to D converter is chapter 35. It starts at page 1729. So, if I were to ask you some questions about how to do an analog to digital conversion by first, as I said, initializing your control registers and then actually doing some measurements, you would go to this section and it would give you some ideas of how you could do it. So here, successive approximation method, what we covered in class. There's 2 units, interesting. Each unit has 4 channels. There is 10-bit resolution for this particular unit. Then this tells you how it operates. Single mode, A to D conversion is performed once on the analog input of a specified channel. This is often what we call one-shot. Or you can continuously scan up to 4 specified channels. Software trigger, external trigger functions. So let's take a look at how you set these up. As always, and then this is more information I'm not going to get into, but we'll look at this a little bit later. This is the hardware definition of it. It's a little bit different than the one I showed earlier. But again, look, it had, you know what, I'm going to go up to the 12-bit one since that's the picture I showed earlier. So here we are, 8 channels. Successive approximation, 12 bits. Conversion time, 1 microsecond per 1 channel. When you're running at 50 megahertz for your peripheral clock. And again, single cycle scan. A to D conversion is performed for only once on the analog input of up to 8 arbitrary selected channels. So it looks like you can just say, measure all 8 once, and then you'll be able to go and read that. So in this case, you can, I'm going to go down, here's our picture. Again, we have the 8 channels. We have the high reference, the low reference, right there. Here's an external trigger right here. Now, it will start telling you if you want to access the data register, well, here's this physical address. So in other words, your A to D conversion may come in on pin AN0, but when you want to read that data, the actual symbol that you write in your code is ADDR0. A to D data register 0. Then look here, there's a couple more control registers. ADD or ADCR or CSR. Channel select registers, extended registers, etc. Now on the rest of the pages of the manual, it may give you a little bit of description. So in this case here, it tells you A to D registers. Now how many bits would this be? These registers, they say, are 16-bit read-only registers. But if we're doing a 12-bit A to D conversion, what does that mean? The higher 4 bits may not be valuable for you to take a look at. So maybe you will need to use some masking to eliminate those. So what I would point out with is that maybe when you are doing some reading, after you've initialized your ADC control register, you will initiate a read, and then you will actually read the data and use it. So the easy thing is, if we're going to read the data and use it, one of the easiest things we could do is we could just say error rates. Maybe we will work with our ADDR. And we'll use, let's say 0. And then we'll want to end it with what? 0 hex, 0 FFF. And that way it will mask out the lower bits. And then we could do something like we could store it as ADC value. Now that's not exactly what the definition is in our case, but I just wanted to show that to you as an example. There's some examples in the book as for what this exactly will appear like. All right, so we said for our ADC conversion, initialize, read, initialize the control registers, initialize a read, and then read the actual value. So in this case, this is reading the value. So let's go back to our book. So back in our manual, you will have showing up several examples of what it looks like. So here's what it looks like. It is, the top bits are going to be unknown, and everything else is going to hold data. And that will be your 12-bit converted data. Let's see, you know what? We don't need this anymore. So I'll make this a little bit bigger. Can you see that okay? You need it to be bigger? Is anybody going to talk? How about that? Is that better?
Perfect.
Yeah, I'll go up a little bit more. There we go. Because that's the width of the page. Now, interesting enough, you can actually identify if you want it aligned to this side over here, or if you want it aligned to this side over here. So that's one thing that you're going to have to make sure you set in your control registers. Let's take a look at some other control registers that you might have. Oh, look at this. There's a 14-bit A to D converted value. That's what they call what's addition mode. I don't want to go into that right now. All right. So here's the A to D control register. And what will, have I never showed one of these to you guys before? No? All right. So here's exciting. Here's exciting. Remember I said you could start your conversion based on your internal clock that's running or some external clock signal that comes in on a pin. This is where you identify it. So if you actually wire something to that outside pin, there it is. That tells you what it's going to be wired to. And so you would put a 1 here if it had an external trigger, a 0 otherwise. Then there's something called trigger enabled. And this actually helps you to say, will you or will you not scan and then do the external trigger. So first you're identifying that you will use an external trigger, And then you actually set up as to let me start running with it. So if you start with a to D with the internal, then this won't even make any difference. You can identify how fast you want to work with, either the peripheral clock, or you can divide the peripheral clock by 2, by 4, by 8. In other words, if you want to go slower in your A to D conversion, you could do that. This is having to do with interrupts. I'll wait for that later. Remember how I said you could just do a single scan, or you could just continuously scan? That's where you set it. And then this bit, ADST, identifies when you want to start and stop a conversion. Because, let's imagine this. You can do all of your setup for all of your registers. A to D conversion, and we'll see later, serial, and maybe some other peripherals that you have. But you don't really want to start any of the work until you get into your while loop. So in your while loop, you may actually set your bit to say, let's start the conversion and let's go. That's just one of the registers. And by the way, you can set each of one of these individually, or you can set them by you can set them all at the same time. So if you had something like, all right, let's take a look at this. What if we want to say, I want to use the P clock divided by 8. My trigger is going to be internal, so I don't have to worry about this as well. I don't have to worry about interrupts. I'm going to do a single scan, and then I don't want to start it up yet. So in other words, all of these bits are going to be 0. So my line that I would write would be something like what? My line would be initializing the control register. It is the AD CSR that we want to work with, right? Now, as it turns out, we have a couple of different units that we can work with. So in this case, we have our A to D converter 0. And oh, by the way, this is only a byte. So we'll work only with a byte. And we want to set that to all zeros. Now, if we look again at our book, there's another register that you have the ability to take a look at, and that would be the well, here's one that identifies which channels you're going to work with. So if you say, just give me one shot, all right, so scan everything or continuously do it, you can actually say which one of these channels you want to be assessed or to be read every single time or to be converted every single time. So if you want to, you can actually identify one or more of these channels. All right, so what else? I want to go over that one, because that makes it a little bit more control or more confusing. There are other things that you can do which in the book also gives you some advice on what else. I am looking for ADCR. I'm going to have to go down to identify what that is. the other things is when you're starting to look at hardware, it gets a little bit more complex. So what I will do is I will give you the following information to ponder for the upcoming exam. And that is, if you have the following setups of code, what do you think this does? Well, we already talked about this line right here. That's how you set up the register. Oh, look at this. That's the same register, but we're looking at a single bit, and the ADST said what? Start a conversion, right? And we set it to 1. So that means that we're setting up the registers that we will be using to read the ADC value, and then we start converting. And then perhaps right here, oh, look at this. If ADCSR bit ADST is equal to 0, so in other words, when it has done its conversion at once, it will set that bit to 0. And so when you see it, and I is equal to 0, then it's going to go through and it's going to read the value, output it, I++. It's going to increment. So what does that mean, I++? All right, so it adds 1 to I, which means that this code will only run once. The while loop will go forever. This line will only execute 1 time after a single ADC was read. All right? Now, I wrote this down for quiz number 9. I tell you what, I'm not going to make this quiz number 9, but I'm going to hand this to you, and you can feel free to look at this and play, and perhaps even study it really carefully, because you never know when something like this will appear on a test. All right? With that, we're going to say that's it for the class. You can turn that off.